Hello, my organic chemists. Today we are going to talk about organic reactions. There are many hundreds of organic reactions, but we are only going to talk about just a few of them, I think 6 of them this year. So the first 2 types of these organic reactions we're going to study happen with alkanes. Alkanes are the reactants. Remember, alkanes are the ones that have single bonds all over. They're saturated with hydrogen, so they're just carbons and hydrogens with all single bonds. So the first type, you know that you have a substitution reaction if your reactants are an alkane plus a halogen. So let's write that down. Reactants are alkane plus a halogen. Now, how would you know that you have an alkane? Because a lot of these are just like, hydrocarbons. How would we know? Well, if you're given the structure, you can tell because they're all just carbons and hydrogens and they're all single bonds. But what if you're given the formula? Well, if you're given the formula, one of 2 things. Either draw it out so they can look at the structure, or see if it fits into the alkane CnH2n plus 2 formula. So CH4 fits in that CnH2n plus 2, so that is an alkane. C2h6 fits in that CnH2n plus 2, so that is an alkane. So that's how you know that it's an alkane. What are halogens? Halogens are group 17. So those are chlorine, bromine, fluorine, and iodine. So any of those 4. So let's draw this methane so we can see what happens. So methane looks like this. It is the simplest organic molecule. Methane is natural gas. And we are reacting this with Cl2, which looks like this. Now this is called substitution. That means one thing takes the place of something else. It substitutes it. So what's going to happen here is one of these hydrogens, any of those, just one of them, is going to be substituted by one of the chlorine atoms. So those 2 are going to substitute each other or switch places. This one and this one are going to switch places, right? So what are the products? So the product for this would be, there's my CH4, but now I have a chlorine in it instead of a hydrogen. And then my byproduct is HCl because both of these switched places. So now this has a chlorine here and this has a Cl there. So this is the structure for it. If you just wanted the formula, it would be CH3Cl plus HCl. So this is the same thing as this, and this is HCl, of course. Now, this could occur more than once. So if I tell you this happens again, so if I react this with another Cl2, for example, I could switch another hydrogen with a chlorine, and a third, and a fourth, and so on. So if it doesn't say anything, that means it just occurs once. So one hydrogen is substituted with one chlorine. But if it tells you how many times, then that's how many times you do it. For example, I have C2h6 plus Br2, and it says I'm going to do that 2 times. So that means that I really have 2 of these bromines that I'm reacting with it. So again, that means that 2 bromines are going to substitute 2 hydrogens because that tells me that it's occurring twice. So what I would have is C2H. I originally had 6 hydrogens. 2 of them are going to be substituted, so I'd have 4 left. And those 2 hydrogens are now substituted by 2 bromines. And then I'd have 2HBr as my byproduct. Let's look at the next one. So the next one, I have C2H6 reacting with F2, but I'm going to do that 3 times. So that means I'm going to substitute 3 hydrogens with 3 fluorines. So C2 H, originally I had 6. 3 of them are going to be substituted, so I have 3 left. And those 3 hydrogens that were substituted are substituted with 3 fluorines. And then I have 3 HF left over as my byproducts. Next one, I have C2h6 plus I2, and I'm going to do that 6 times. 6 times. So my products are C3H, let's see, I started out with 8 hydrogens. I substituted 6 of them, so I only have 2 left. And those 6 hydrogens were substituted with 6 iodines. And then, as my byproduct, I have 6 HI left. So we're substituting a hydrogen for a halogen. So I wrote down here what I just said, that in a substitution reaction, you substitute 1 hydrogen atom with 1 halogen atom. I should maybe add in an alkane. All right, let's look at the second type of reactions, also happening for alkanes. This time, you are going to start with an alkane and heat it up with this catalyst here, chromium 3 oxide. So you'll see heat and this catalyst with the alkane. This is called dehydrogenation reaction, and let's think about what this means. Well, hydrogenation means adding hydrogen. D means not. So, or the opposite. So dehydrogenation means that you are removing hydrogens. So for example, hydrated means that you are with water. Dehydrated means you're without water. It's the opposite. So dehydrogenation means you're removing hydrogen. And in this case, we are removing 2 hydrogen atoms, one from each, so we're removing a hydrogen atom from 2 adjacent carbons, basically. So we're removing a total of 2 hydrogens, one from each carbon, with the 2 carbons adjacent to each other. Let's write that down. So you're removing 2 hydrogen atoms from adjacent carbons. So let's look at the first one here. We have C2H6, and we are heating it up and adding this catalyst, which tells us we are dehydrogenating it. So you pick 2 carbons that are adjacent to each other. Obviously, there's only 2 carbons here. And you take 1 hydrogen from this carbon away and 1 hydrogen from this carbon away. So it doesn't matter which one, which hydrogen, as long as you take 1 from each of the carbons that are adjacent to each other. So let's take this hydrogen, cross it out, and this hydrogen, cross it out. So my product would look like this. This is what's left. 2 carbons bonded together, and each of them have 2 hydrogens. Well, what's wrong with my answer? Well, remember, carbon needs 4 bonds to be stable, right? Right now, each carbon has only 3. So what happens? Well, what happens is it forms a double bond. If you do it again, maybe you can form a triple bond. So if I tell you, hey, I'm going to do this twice, then after you form this, you're going to take another hydrogen from this carbon, another hydrogen from this carbon. Those 2 are going to be removed, and you'd make a triple bond. Again, if it doesn't say, then you just assume it happens once. So you go from your alkane to your alkene. Let's look at the next one. So the next one, I'm given an alkane, and I'm adding heat and this catalyst that tells me it's going to dehydrogenate it. I'm going to remove hydrogens. So I find 2 adjacent carbons. In this case, it doesn't really matter. I could pick those 2 carbons or those 2 carbons. Again, does not matter. So let's just say I'm going to pick those first 2 carbons here. What you cannot do is you can't pick this carbon and this carbon. They have to be adjacent to each other. They have to be next to each other. So let's pick those 2. I'm going to take away a hydrogen from this carbon. So let's say I'm going to take this hydrogen away. And I'm going to take a hydrogen from the next carbon. So it doesn't matter which one. Let's pick this one. And so let's see what we would end up with. So I have my 3 carbons here. This one, the first one now has just 2 hydrogens on it. The second one only has 1 hydrogen on it left. The last one has 3 hydrogens. So what's wrong with this? Well, these 2 carbons only have 3 bonds right now. So because we remove this hydrogen, I make a double bond here. So this is actually double bonded. So I go from an alkane to an alkene. Again, I might do it again and form an alkyne, and so on. So for alkanes, we have the 2 types. We have substitution, and then we have dehydrogenation. Let's look at alkenes and alkynes. So if I have a triple bond or a double bond in my reactant, we have 2 types of reactions here. The first one is called hydrogenation. So that sounds kind of familiar, right? We just did dehydrogenation. This one is hydrogenation. So guess what? This is the opposite of this one. So instead of removing 2 hydrogens, I'm going to add 2 hydrogens to adjacent carbons. So adding 2 hydrogens to adjacent carbons. Now those 2 adjacent carbons need to have a double bond or a triple bond between them. So let's look at this one here. I have an alkyne, and I'm going to add H2 to it. So when you have an alkene or an alkyne and hydrogen is added to it, that's how I know it's a hydrogenation reaction. So if I see a double bond or a triple bond plus H2, that's how I know that I have a hydrogenation reaction. If I'm adding hydrogen, that's kind of obvious what type it is. So what you do is you pick the 2 carbons that have a double or a triple bond between them, and you add a hydrogen to each of those carbons. So you add a hydrogen to this one here, and you add a hydrogen to this one here. So what's the problem with that? Well, now each of those 2 carbons have 5 bonds. That's not okay, because each carbon needs 4, right? So what happens is one of these bonds break and it becomes a double bond. So let me write that down for you. So I'm going to rewrite what I had first. There it is. I'm going to add a hydrogen to this carbon, a hydrogen to this carbon, which makes one of these bonds break. And so I end up with a double bond. So that's my product. I could do it another time and add another hydrogen here and another hydrogen there. Guess what? We'd form an alkane. Let's look at this one here. So now I have an alkene, a double bond, and I'm going to add hydrogen to it. So I find the 2 carbons that have a double bond between them, and to each of those carbons I add a hydrogen. Well, what's wrong with that? I have 5 bonds, so that means one of these bonds break. So I end up with an alkane. So my product looks like this. So initially, each one of these carbons had 2 hydrogens. Now they have a 3rd hydrogen in each of them. So that's hydrogenation. Halogenation is very, very similar. Except instead of adding hydrogen, I'm adding halogens. So instead of hydrogenating it, I'm halogenating it. So here, I will have a double or a triple bond. So you'll see double or triple bond plus a halogen. That's how you know that you have a halogenation reaction. So what you do is you add 2 halogen atoms to adjacent carbons. And those adjacent carbons need to have a double or a triple bond between them. So in this case, I'm going to add chlorines. So I add a chlorine to this one, a chlorine to that one, and you'd have to break one of these bonds in order to do that. So you end up with a double bond, CH3Cl, and it honestly does matter where you put the chlorines, but for now, don't worry about it. Just know that you have 2 chlorine atoms there, and it makes it a double bond. Let's look at the next one. The next one I have bromine that I'm going to add, so I'm going to add a bromine to this one, and bromine to that one, and I'd break one of these bonds. So I end up with each carbon having 2 hydrogens and a bromine. And again, it does not matter where you put it for now, for this here. Okay, next type of reactions is one that we've studied before. It is combustion. So this is not new. Combustion of hydrocarbons. And in combustion of hydrocarbons, we studied that to know a combustion reaction has occurred for a hydrocarbon is that you find an organic molecule, so something that has carbons, hydrogens, and maybe oxygens as well, and you add oxygen to it, so any organic molecule plus oxygen, and you yield carbon dioxide and water. Now, don't let it intimidate you. I could give you any type of organic molecule. So I could give you this and add O2. I could give you this and add O2. I could give you something as simple as this and add O2. Any organic molecule plus O2 is going to give you CO2 and H2O, and it's going to be combustion. So for these, it's pretty easy what the products are. They're always going to be the same, right? The tricky part about it is balancing it. So let's go ahead and try to balance this one. So I'm going to need 2 of these, 4 of these, 6 of these, and then 7 O2. Next one, again, CO2 and H2O. So let's see, 2 carbons, 4 hydrogens to make that a 2, and then 3 O2s, and that should be balanced. Okay, last one. Again, CO2 and H2O. And let's see, we'll need 2 carbons, 6 hydrogens, so 3. And then for the oxygens, we have 2, so 3. That should be good. That's 7 hydrogens, 7 oxygens on both sides. So the hardest part about this is just balancing, but it's not anything new. Hydrocarbon plus oxygen gives CO2 and H2O. That one's not new. The last type of reaction is one of my favorite organic reactions. It's called esterification. And in one of my videos, when we were talking about functional groups, we talked about esters. So esterifications mean that you are making esters. And esters are the organic molecules that have nice scents. So we talked about, a staple in organic chemistry lab is making isopentyl acetate, which is the smell of bananas. If we were in the lab, we would have an esterification lab and we'd make all kinds of different scents. The cool thing about this reaction is that you start out with an alcohol and a carboxylic acid, and both of those stink. Both of those smell very, very bad. But the product is an ester and water, which smell, pretty good. So it's a pretty cool lab. The only thing about it is you don't want to have any excess reactants or any limiting reactants because you don't want any left over of your reactants, and you want your reaction to go to completion, so you just end up with the good smelling stuff, because if you end up with any leftover reactant, then, it's going to be a bad smell mixed with a good smell, which, ends up being bad. Anyway, in lab, in college, when you make your isopentyl acetate, you make it one day, and then you spend another lab day, like 3 or 4 hours, basically purifying it, isolating it from any catalyst that you added, any of the starting reactants and all that. So what you do with esterification reactions, first to recognize that you find an alcohol and a carboxylic acid. So let's look at this. This is a carboxylic acid because I have a carbon double bonded to an O and then an OH. So that makes it a carboxylic acid. Remember, this hydrogen is the acidic hydrogen, right? For an alcohol, I know it's an alcohol because I just have an OH without the C double bond O, right? Just an OH. So there's my alcohol, there's my carboxylic acid. What happens is I form water plus an ester. So what you do is it's the carboxylic acid is an acid, right? So it gives away an H. So you take that H out. The alcohol, you remove its OH, and the H plus the OH will make water. And then whatever is left of both molecules, you kind of join together. So I'm going to draw this part right here. So I have a C double bonded to an O, and it has an H on this side and an O on that side, right? We removed the H, but we still have the O. In the other molecule, we removed this OH, so this is what we have left. So carbon with 2 hydrogens, and then carbon with 3 hydrogens. And so this is my water, and this is my ester. Remember, an ester is where you have a C double bonded to an O, and then an O and a C. So it kind of looks like a ketone with a C double bond O, but it also looks like an ether because there's an O in between 2 carbons there. So this is called ethyl formate, and it's an ester. All right, let's look at the next one. Now, the next one looks kind of scary, right? This is a pretty big molecule. Don't let that intimidate you. All you care about is this part right here. C double bond O and an OH, that tells us it's a carboxylic acid. This one, that's an alcohol. So I see carboxylic acid and alcohol, that's an esterification reaction. So I remove this hydrogen here, this OH right here, and that gives me water. And then I link the rest. So let's see. This one right here, you have a benzene ring. And if you want, you can just put a circle in there instead of your alternating double bonds. That benzene ring is then bonded to a carbon, which has a double bond O, and then another O. The other molecule, what I have left of it, is just a C with 3 H's. And there you go. There's your ester right here. This part is what makes it an ester. Let's look at the last one. Again, don't let the shape or size of the molecule intimidate you. You see that you have a C double bond O and an OH. That tells us it's the carboxylic acid. All this doesn't matter. What matters is the OH. That tells us it's an alcohol. So what we're going to do is we are going to take out the H from the carboxylic acid, the OH from the alcohol, and that's going to give us H2O. And then my other product is going to be whatever is left of those molecules. So let's see, I have a C double bond O, I'm trying this one here, and a CH2, CH3. On the other side, I just have an O. And now I'm going to draw this. So this is where it connects here. So that's this carbon. So that carbon is bonded to an H on the bottom. a CH3 on top, and a CH3 on the side. And that is my ester. So again, don't let all these shapes intimidate you. All you care about is the H and the OH. Remove those and then link the two, and there's your ester. Again, there are hundreds of different types of reactions, but these are the 6 that we are studying this year. I hope this helps. Have a wonderful rest of your day.